AI models today can solve complex problems, write flawless code, and score over 95% on standard benchmarks. But what happens when the rules change? Are they truly thinking, or are they just reciting what they have already seen? To understand this, we start with a simple system: Conway's game of life. It is a two-dimensional grid where each cell exists in one of two states: alive or dead. The system evolves step by step in discrete moments called generations. In this standard universe, each cell looks at its 8 immediate neighbors: horizontal, vertical, and diagonal. It then follows 4 immutable rules. Rule 1. If a live cell has 2 or 3 neighbors, it survives. Rule 2. If a dead cell has exactly 3 neighbors, it becomes alive. Rule 3. All other live cells die. Rule 4. All other dead cells remain dead. The intuition is simple: too few neighbors, the cell dies of underpopulation. Too many neighbors, it dies of overpopulation. Just the right number, it survives. And with exactly 3 neighbors, conditions are perfect, and new life appears. From these rigid, simple rules, infinitely complex patterns emerge. One of the most famous patterns is the glider, a small cluster of 5 cells that moves diagonally across the grid, shifting and shifting until it returns to its exact original shape, 4 generations later. Now, here's the problem. Modern large language models have seen Conway's game of life millions of times in their training data. They have memorized the gliders, they have memorized the blocks. They don't just understand this system, they remember it. It is an instinct. So, what if we change the rules? Not completely, just slightly. This is corrupted Conway's game of life. It is the exact same system, but with one critical rule changed at a time. This isn't just a logic test, it is a perfect test of something deeper: inhibitory control. Can an AI suppress its trained instinct, abandon its memorized answers, and follow a new reality? Instead of standard play, we introduce 10 specific mutations that alter the fabric of the simulation. We tweak the exact number of neighbors required for birth or survival, instantly shattering memorized patterns and triggering chaotic, explosive growth. We alter the spatial neighborhood, restricting how cells see each other. We even inject temporal mutations, where time freezes, or the rules alternate back and forth on every single step, creating an agonizing working memory load that forces the AI to constantly suppress its training. Using these mutations, we created a 600-task benchmark generated entirely programmatically. Different grid sizes, different step depths, different adversarial patterns. We fed these exact, corrupted coordinates to frontier AI models. No ambiguity, no guessing. Either the model traces the new rules perfectly, or it fails. And here's what happens. When the rules change, AI performance catastrophically collapses. But they do not fail because they lack the capacity to reason. They fail because they cannot ignore what they have already learned. We discovered a phenomenon called the pattern trap. When we fed models a random scattering of cells, they struggled. But when we fed them a classic, named pattern, like a glider, and applied a mutated rule, they actually performed worse on the hardest mutations. The moment the AI recognized the familiar glider, its memory hijacked its logic. It confidently hallucinated the standard game of life outcome, completely ignoring the new rule in the prompt. Memory helps, right up until the moment it becomes a liability. Current models are brilliant mimics, but true artificial general intelligence cannot just rely on crystallized knowledge. True intelligence isn't just knowing the rules, it's having the cognitive control to know when to override them.